What if an interstellar object whirling through our solar system is actually a nuclear-powered spacecraft sent by aliens to test how humans respond?
Something just messed with the sun, and scientists are freaking out.
NASA detected a mysterious object speeding toward Earth. And some actual bona fide experts think it might not be your typical space rock, or maybe any kind of rock, or a natural phenomenon at all.
On September 19th, astronomers spotted a mysterious object from deep space tampering with the sun's magnetic field.
We've got some fresh images of 3I Atlas, a third ever interstellar object observed from Earth, currently racing through our solar system.
Minutes later, a solar flare erupted, triggering radio blackouts over Earth. But here's the kicker. It wasn't a solar system object. It came from beyond.
Third ever interstellar object we've detected. That just means it came from outside of our solar system, a visitor from beyond.
And what it's doing next might shock you even more. Stick around, because when you hear what this thing is made of, you'll be speechless. What happened to the sun? While 3I Atlas makes its historic journey through our solar system, the sun has been particularly active during this solar maximum period. The timing creates an incredible opportunity. For the first time ever, we can study an interstellar visitor during a period of peak solar activity, giving us unprecedented data about how solar radiation affects these ancient objects from other star systems. On September 19, 2025, about 93 million miles away, astronomers observed that the sun was unusually active. At exactly 9:21 p.m., the active sunspot region AR4216 emitted a solar flare classified as M1.5. For those unfamiliar, that designation is part of how scientists rank flare intensity. They use letters A, B, C, M, X, with each letter representing about a 10-fold jump in energy. So an M-class flare is not the very strongest, but it is certainly capable of creating measurable effects on Earth. That particular flare was intense enough to ionize parts of Earth's upper atmosphere and trigger a radio blackout in the HF band, what scientists call an R1 event, over a region of the Pacific. What makes AR4216 interesting is its beta-gamma magnetic configuration, a more complex and unstable field geometry. Regions like that are more prone to magnetic reconnection, which is how flares release energy. When such magnetic structures become stressed, they can erupt, giving rise to electromagnetic bursts, the solar flares. So when AR4216 reached a tipping point, this flare was the result. Meanwhile, 3I Atlas was first spotted on July 1st, 2025, by the Atlas Survey Telescope in Chile.
3I Atlas has a tail. The MPC reported a tail spanning 3 arcseconds across the sky at an angle of around 280 degrees.
From early observations, astronomers realized its orbit was hyperbolic, meaning it's not gravitationally bound to the Sun and is passing through from interstellar space. Its name reflects that, 3I for the third interstellar object detected, Atlas for the survey that found it. No doubt 3I Atlas is interesting on its own. It behaves like a comet. It has a nucleus, outgasses, produces a coma, and shows a tail. Observation, including from the James Webb Space Telescope, suggest its coma is unusually rich in carbon dioxide, more so than many comets native to our solar system.
This comet is now venting a mixture of gases from its nucleus, as well as streams of dust and ice fragments.
Other detected components include water, carbon monoxide, carbonyl sulfide, dust and icy grains, and in some cases, heavier volatile gases such as atomic nickel vapor or cyanide. As for why solar flares happen and how they affect Earth, the energy from a flare travels at the speed of light, so it reaches us in about 8 minutes. That burst of X-ray and extreme ultraviolet radiation ionizes the lower layers of the ionosphere, making those layers more absorbing of radio waves instead of letting them bounce. That absorption is what leads to a high-frequency radio blackout, disrupting long-distance radio communications for a period.
Now, it could be that 3I Atlas hasn't been exposed to the sun enough to begin water ice sublimation, which would raise activity levels.
So, during that blackout window, ships, aircraft, or amateur radio operators using shortwave radio in the affected region might have experienced static, fading signals, or even total signal loss. Because it was an R1 event, though, the disruption was minimal and short-lived. This flare and blackout gave scientists a timely snapshot of solar behavior under active conditions. And with 3I Atlas passing through at the same time, researchers now have a rare chance to study how an interstellar body interacts with a more volatile, highly energetic solar environment. 3I Atlas. But here's where 3I Atlas gets truly extraordinary. In recent weeks, it's been brightening faster than predicted, outperforming standard comet models as it warms and releases material. When astronomers revisited their data, they found that the comet's nucleus size remains uncertain, thanks to interference from its thick coma. Estimates place it somewhere between 2.5 and 3 miles in diameter, though some observations suggest it might be even larger. Based on the coma's brightness and other indirect methods, some models even allow for sizes up to tens of kilometers, though that remains speculative. It's also moving incredibly fast, roughly 38 miles per second relative to the Sun, or about 140,000 miles per hour. Its path brings it to perihelion, the closest approach to the Sun, around October 29, 2025, when it will pass just inside Mars's orbit. Before that, on October 3, 2025, it will swing past Mars at a distance of 19 million miles, and ESA's Mars Express and ExoMars Trace gas orbiter intend to turn their instruments toward it.
So here's the deal. It's normal for a comet to accelerate when it passes by the Sun.
As 3I Atlas approaches the inner solar system, its coma and brightness are changing rapidly. The ratio of CO2 to H2O appears unusually high. Even when it was 3 to 4 astronomical units away, it already showed signs of activity. Water ice alone wouldn't normally sublimate strongly at that distance. That suggests there may be volatile ices other than water on or beneath its surface, or other mechanisms like small icy grains breaking off, helping to drive its activity. Finally, its tail is growing, and its coma has been observed across multiple wavelengths: ultraviolet, optical, and infrared, giving astronomers more clues about the composition and structure of the gas and dust envelope. In particular, the CO2 emissions seem to extend farther than other components. Now, its trajectory takes it to its closest point to the Sun, which is called the perihelion, around late October 2025, exactly around October 29th, where it will pass just inside Mars' orbit. What this means for Earth. Now, the timing between the series of the changes in the Sun and 3I Atlas's sudden brightening is impeccable, and it creates a rare scientific window for scientists. This alignment offers astronomers a unique chance to watch how intense solar radiation interacts with an interstellar visitor in real time. During solar maximum, the Sun is more active. More sunspots, more flares, and more coronal mass ejections. That heightened space weather means that observing 3I Atlas now gives us the best shot at measuring how solar particles and fields affect its coma, tail, and emission processes. Things we've never seen this clearly for an interstellar object before. Part of what makes this exciting is that solar activity also sets the stage for auroras on Earth. When charged particles and plasma from solar events hit Earth's magnetosphere, they light up upper atmospheric gases in dazzling colors: green, red, and purple, especially near the poles. More frequent solar storms during a peak cycle increase the odds for visible auroras.
Twisted and unstable, desperate to spew their energy, they create a magnetic bomb primed to explode.
Of course, seeing them depends on many factors: whether a solar event sends particles toward Earth, how the magnetic fields align, how strong the storm is, and whether local conditions like weather or light pollution cooperate. Many flares don't produce Earth-directed effects, so auroral displays might still be rare or subdued. From a research perspective, this convergence is golden. By correlating solar activity with the comet's behavior, scientists can track how flares, solar wind variations, and coronal mass ejections influence the gas and dust around 3I Atlas, possibly changing its outgassing rates or tail shape. They can also compare how an interstellar object reacts to solar forces compared with ordinary comets born in our own system. And because spacecraft and telescopes know when solar storms are likely, they can time observations to catch transient changes in the comet's emissions or dynamics. Currently, scientists are monitoring solar wind parameters, coronal holes, and active regions because those are key to predicting geomagnetic storms and anticipating when Earth-comet interactions might become especially active. In short, while 3I Atlas isn't stirring the Sun itself, its passage during a particularly noisy period of solar activity gives us an unprecedented observational laboratory. If a major solar event happens at the right moment, we might witness interactions between interstellar material and solar forces in a way never captured before. Disruptions in our planet. Unfortunately, these solar flares do much more than we recognize. They affect life on Earth. When the Sun fires off flares, coronal mass ejections, energetic particles, or disturbances in the solar wind, those bursts of energy travel through space and interact with Earth's magnetic field and atmosphere.
And coronal mass ejections, vast clouds of magnetized solar plasma and radiation leaping into space.
One big effect: radio blackouts. When a strong flare sends lots of X-rays and extreme ultraviolet light our way, it hits the ionosphere in about 8 minutes, ionizing its lower layers and increasing the density of charged particles. In those conditions, instead of reflecting radio waves, parts of the ionosphere absorb them. That's what knocks out high-frequency radio communications, what's classified as an R event. Satellite and GPS systems are also vulnerable. The signals they send down must pass through the disturbed ionosphere. When that layer is turbulent or overloaded with electrons, GPS accuracy can degrade or even lose lock entirely. There's also ionospheric scintillation. Rapid, small-scale fluctuations in electron density can make satellite signals flicker or flutter, making navigation, mapping, and aviation more difficult. Electrical grids can suffer too. During strong geomagnetic storms, changes in Earth's magnetic field can induce currents in long conductors like high-voltage transmission lines. These geomagnetically induced currents stress transformers and substations, sometimes causing disruptions or damage.
Solar material gets launched into space. In the case of the flare, this happens quickly. The Carrington event was only 5 minutes.
During strong solar cycles, these effects don't always stay near the poles. Geomagnetic disturbances can push toward mid-latitudes, putting countries further from the poles at risk too. Satellites in low Earth orbit can also be hit in another way. When solar heating makes the upper atmosphere expand, it increases drag on spacecraft, potentially altering orbits or requiring extra fuel to maintain them.
On Arctic nights, the aurora often flames across the winter sky. What is it, and where does it come from?
Because we're entering a more active solar period right now, these space weather risks are more likely, not just theoretical. We may see more frequent radio blackouts, GPS glitches, satellite disturbances, or grid stress. The challenge is predicting when and where they'll strike. While 3I Atlas is still leaving scientists confused, there are two other interstellar objects that we should probably keep an eye on. 1I Oumuamua. In October 2017, astronomers using the Pan-STARRS 1 telescope in Hawaii caught a faint, fast-moving point of light. They designated it 1I 2017 U1, later given the name Oumuamua, which in Hawaiian means a messenger from afar arriving first. By the time it was discovered on October 19th, it was already heading away. It had passed its closest approach to the Sun on September 9th, 2017, at about 0.25 astronomical units, roughly 1/4 the distance from Earth to the Sun.
Scientists began to try and explain what was pushing Oumuamua. A few initial hypotheses were quickly ruled out.
What immediately caught scientists' attention was its orbit. Oumuamua's path is hyperbolic, meaning it is not bound by the Sun's gravity. It came from interstellar space and will eventually leave again. When it comes to its size and shape, astronomers have been unsure. Depending on how reflective it is, estimates place its dimensions somewhere near a mile or less, though these are rough. Its light curve, the way its brightness changed as it spun or tumbled, showed extreme variation. That suggests it is not a simple, uniform shape. One face might present a wide, bright surface, another, a narrow or darker one. That kind of brightness swing hints at a highly elongated or flattened shape, and a tumbling motion rather than smooth rotation. Originally, many people imagined Oumuamua as a cigar shape, long and thin, perhaps 10 times longer than it was wide. But later analysis has also considered a disc-like or pancake shape as a better fit to some of the observations. Its color is reddish. It reflects light in a way similar to objects in the outer solar system, just like Kuiper Belt bodies.
While these objects are interesting, they don't settle the question of Oumuamua's nature, and there's much we still don't know. For example, where did it come from?
That reddening likely comes from long exposure to cosmic rays and space weathering, possibly coating its surface with complex organic molecules. Now, here's where it gets truly odd. Many comets show outgassing, when icy components sublimate near the Sun, releasing gas and dust, creating a coma or tail, and sometimes pushing the body slightly, which is what scientists call non-gravitational acceleration. Oumuamua exhibited a small non-gravitational acceleration as it moved away from the Sun, an extra push beyond what gravity alone would predict, but no visible tail or coma was clearly detected. This mismatch triggered many hypotheses. One is that there are very weak, low-dust volatiles sublimating in a way that doesn't leave a detectable gas or dust cloud.
A comet with a visible tail and composition resembling comets within our solar system.
Another, more exotic idea from Seligman and Laughlin is that Oumuamua contained molecular hydrogen ice, which sublimates so cleanly it produces thrust without the usual signs of a cometary tail. Some others have proposed nitrogen ice or other exotic ices or surface structures. Because observations were limited, it was already receding rapidly. Many properties remain uncertain. Its exact shape, mass, how much ice or volatile material it held beneath its surface, and even where it came from before entering our system.
However, in 2017, an interstellar object passing through our solar system was detected for the first time.
Where did it originate? We don't know. Backtracing its path gives a few candidate directions toward nearby stars, but none definitive. It may have wandered through interstellar space for millions or even billions of years before stumbling into our solar neighborhood. And that brings us back to 3I Atlas. The lessons we learned from Oumuamua, how to spot fast interstellar intruders, what signatures to watch for, and how unexpected behavior can reveal exotic composition, helped astronomers refine their surveys and analysis. In a very real sense, Oumuamua taught us how to see 3I Atlas coming. 2I Borisov. And just when astronomers thought they'd grasped what an interstellar object could look like, Borisov arrived in 2019 and changed the game all over again. In late August 2019, Crimean amateur astronomer and telescope maker Gennady Borisov spotted something peculiar through his homemade instrument. On August 30th, he first designated it C-2019 Q4. Very quickly, scientists realized this was no ordinary comet. Its trajectory marked it as an interstellar intruder. Thus, it was renamed 2E Borisov, the second confirmed interstellar object after Oumuamua. Unlike Oumuamua, which was only discovered after its closest approach to the Sun, Borisov was caught while inbound. That gave astronomers precious extra time to scrutinize it before it faded from view. Its path is hyperbolic, so it's never bound to the Sun. It's just passing through. Its perihelion, that is, its closest approach to the Sun, occurred in early December 2019, and shortly thereafter it made its closest pass to Earth in late December. When it comes to size, estimates remain rough. The nucleus itself was too small to resolve clearly, hidden behind its bright gas and dust coma. Some analyses constrained its radius to under 1 mile, assuming a low albedo. From indirect inferences, many put the size on the order of a few tenths of a kilometer to about a kilometer range. In other words, as big as several football fields. As Borisov neared the Sun, its ices began to sublimate, forming a noticeable coma and tail, behaving more like a classic comet than a bare rock. But the surprises kept coming. Its gas emissions were unusually rich in carbon monoxide, more so than in any comet observed at a similar distance from the Sun. Indeed, the CO to water ratio was anomalously high, implying that the comet retained volatile ices in very cold conditions, perhaps not typical in many solar system comets. Other molecules detected included cyanogen and hydrogen cyanide. Some studies even report atomic nickel vapor in the coma, a metal vapor signature rarely seen so far out from the Sun. By combining observations from ALMA, Hubble, and major optical telescopes, scientists could estimate dust production rates and gas outputs. They noted that Borisov's coma included compact dust grains, also called pebbles, indicating that the comet may have preserved materials from its protoplanetary disk with minimal alteration. In March 2020, Hubble images showed evidence of fragmentation, a piece breaking off the nucleus. That's a familiar fate for comets under stress from heating and outgassing. Where did Borisov originate? We don't know for sure. The chemical clues, especially its rich CO content, suggest it may have formed in an extremely cold, distant region of a planetary system, possibly around a red dwarf star where temperatures remain frigid even in its protoplanetary disk. It's plausible that a massive planet in that system nudged Borisov out, sending it on a long interstellar voyage. Today, Borisov is on its way out of our solar system, never to return. But while it was here, It gifted astronomers with invaluable data that shows us how an interstellar comet might behave, how its composition compares to comets we're familiar with, and what we might expect from future visitors like 3I Atlas. Because of discoveries like Borisov's, astronomers refined their search strategies, prepared better instrumentation, and advanced models that now help us track and study with eyes sharper and expectations broader than ever before. Every interstellar object that we ever discovered is a reminder that as long as our solar system isn't a closed-off bubble, we will have uninvited visitors from time to time. The big question now is whether this is just a passing curiosity, or if it could lead to real consequences here on Earth. What do you think? Could interstellar objects like Atlas end up changing the way we understand the Sun forever? Let me know your thoughts in the comments. I'd love to hear them. And if you enjoyed this video, don't forget to hit that like button, subscribe for more space mysteries, and turn on the notification bell so you never miss an update. There's still so much to be discovered. See you soon.